We are around 30 registered participants, so let's give them a chance to come in. Okay, the numbers are picking up. And okay, let's, we gave a minute. I will stop sharing now. And I think we can, we can start. So good afternoon, everyone. Welcome to this November mini school of NITheP. My name is Francesco Petruccione, and I'm currently the interim director of NITheP. And today it's a great pleasure to introduce to you the speaker of this new mini school. It is Dr. Graeme Pleasance. He's a postdoc at UKZN. And Graeme, I now need to do to check, did his MSc in theoretical physics at the University of Birmingham, but is then his PhD a few years later at University of Sussex, working with Barry Garraway. Yeah, and he's working on open quantum system, which is a topic that is very close to my heart as well. And I was able to convince Graeme to give us a mini school introducing open quantum systems. So Graeme, people are not here to listen to me. They are here because they are interested in open quantum systems. So if you would like to start sharing the screen, you're welcome to start. And for those of you that have not attended NITheP mini schools before, please make use of the Q&A facility at the bottom of Zoom. And Dr. Ilya Sinaisky will moderate the questions during and after the talk. So if there is some urgent question, please pose it, and Ilya will monitor the Q&A facility and ask Graeme to comment on whatever question you might have. Yeah. So Graeme, thank you very much for offering to give this school, and please you're welcome to start.
Okay, well, thank you. Thanks, Francesco, for the kind introduction. Yeah, let me just reiterate what Francesco said. So I'm currently a postdoctoral researcher in the quantum research group at the University of KwaZulu-Natal in Durban. And I'm really pleased to have been given the opportunity to present a introductory mini school on open quantum systems. So let me start by first saying that, well, I'm assuming that most of the people in the audience have some background in quantum mechanics. And in that regard, there are really, or I should say that I'm assuming you have a background in quantum mechanics, but are perhaps not so familiar with open quantum systems. So in that regard, there are really two main goals of this mini school. The first and most important goal is to provide you with a basic understanding of some of the key ideas and concepts in the theory of open quantum systems. And the second goal is to hopefully convince you as to why the theoretical study of open quantum systems is a interesting field of research in its own right. Okay, so a natural question we can begin by asking is, well, why should we be interested in open quantum systems? What's our motivation behind this? Well, it's a kind of perhaps trivial point to make, but one which I think is worth mentioning anyway, is that realistically, all quantum systems are open. So just to clarify, when I say open quantum system, I mean a quantum system which somehow interacts with its surrounding environment. And well, so from introductory quantum mechanics, we're taught that a quantum system can be described by a ket, and the time evolution of this ket is governed by the time-dependent Schrödinger equation. And yeah, so the time evolution is governed by the time-dependent Schrödinger equation. So the kind of more or less underlying the more or less underlying assumptions behind these postulates is that the system that we're describing is completely isolated from the surrounding universe, which obviously in reality, this is never really the case. And what we can expect to find, and what we indeed see, is that the behavior that's predicted by the time-dependent Schrodinger equation is only really an approximation of what we observe in experiment. So in order to be able to model and describe the types of behavior that we observe in quantum systems when we measure and prepare them in the lab, we really need a theory of open quantum systems. So yes, so the second motivation that I've listed more relates to foundational problems or foundational ideas in quantum mechanics, and this is somewhat related to the so-called quantum classical transition. So to kind of explain what I mean by the quantum to classical transition, let me briefly again talk about the time-dependent Schrodinger equation. So suppose we have a quantum system which is prepared in some superposition state. Then and we let this superposition state somehow evolve in time. Then what the Schrodinger equation tells us is that, well, there may be some dynamics involved in its time evolution, but generally the quantum system initially in a superposition state will maintain the initial coherence as it evolves over time. So it's initially in a superposition state, and at some later time we can expect it to still be in some superposition state. So however, so this is obviously for closed systems. When we start thinking about open quantum systems, this what instead happens is that when we observe the time evolution of a quantum system, instead of the system maintaining its initial coherence, what happens is that its interaction with the surrounding environment tends to destroy any initial superposition, and any coherence that's initially in the system in effect leaks out to the surrounding environment. In other words, a quantum system, the longer that we observe it, the more it tends to exhibit classical-like behavior due to the loss of this coherence. And the process by which a quantum system loses coherence into its environment is commonly referred to as decoherence. And since decoherence occurs as a direct result of a system being open to its environment, the theory of open quantum systems then really provides a natural framework to understand and describe the quantum to classical transition and related phenomena. And okay, the last point that the last motivation that I've listed relates to emerging quantum technologies. So for those of you who were in Peter Knight's talk yesterday, I think you heard quite extensively about this, but just to fill you in myself, so in the last decade or so, there's been strong interest in trying to develop and build quantum devices that harness quantum features like entanglement and coherence for information processing and computation, as well as other kind of related things like sensing and metrology. So currently one of the biggest obstacles to developing fully fledged quantum devices, so devices that we want them to work in the way like we want them to really harness these quantum effects like superposition entanglement. The biggest obstacle for us doing that is that the quantum devices that we have at the moment have an inherently limited lifetime over which they can operate, namely due to noise effects and decoherence. So if we want to use these quantum devices, what happens is that any entanglement which isn't seen in the system eventually gets wiped out by these types of due to noise effects and decoherence, due to it being a non-isolated system. So how can we kind of proceed, and how can we say, okay, how can we deal with these types of problems to really build the quantum devices that we want? Well, one approach is to try to model and understand the types of dynamics and noise effects that are present in these systems, and then hopefully to be able to apply our understanding to come up with strategies to build and engineer quantum devices that are more robust against these types of noise effects. And in particular, the theory of open quantum systems has a big role to play in this application. But there are many other motivations, but just for brevity, I list those three. And okay, so in today's lecture, what I wanted to cover was mainly background material relating to the statistical foundations of quantum mechanics. So I apologize in advance for those of you who maybe already know a lot of this material already, but I just wanted to make sure that I provided a sufficient background material before I started actually diving into the theory of open quantum systems itself. So today's lecture is more or less broken down into three parts. The first part is a more or less textbook introduction to quantum mechanics. The second part, I'll introduce composite quantum systems. So this is really the starting point of this is really the starting point when we want to think about open quantum systems. And if I have time at the end, I might briefly touch on some aspects of quantum measurement. Okay, yeah. So this slide just is meant to give you a kind of flavor of what to expect in the coming lectures. So in next week's lecture, we'll start to really apply what I provide you with today to develop some of the basic ideas and ingredients of the theory of open quantum systems. So I won't specifically talk about these things today, but yeah, this is just to give you an idea of what to expect. And then yeah, so in the third and fourth lectures, I don't have an exact outline for those lectures yet, but the idea is so the second lecture is meant to be kind of sort of a broad sort of general understanding of the basic ideas of open quantum systems. And then the third lecture, I'll go into more specific applications and ideas. And then in the fourth lecture, hopefully I'll get to present some of the research that I've been currently working on. Okay. Okay, so let me just review some basic ideas of quantum textbook quantum mechanics. So as I'm sure most of you are aware, a quantum system can be described by a state vector, a ket psi, and this ket is a complex vector belonging to some Hilbert space H. And to this Hilbert space, Graeme, we can, yeah, sorry.
There is a kind of a bar on top of your screen, which is coming from the keynote plane. Do you see it or not?
No,
because we don't see closed systems, we see only half of that phrase.
Okay, I can see the full slide, so maybe I can try. Okay.
Yeah. What if you play here, or have you done that?
I tried that, and so do you still see the bar across the top?
Yes.
Okay. Sorry, I'm not used to using Keynote. I usually use Beamer, so.
I think it's all right. We don't need to read the title, Graeme. Don't worry. We will sort it out for next time.
Okay.
Okay.
Yeah.
Sorry.
Okay. Yeah. Sorry about that. Yeah. On my screen, I can see the full slide, but yeah, apologies for that. Okay. Yeah. Sorry. Yeah. A quantum system, a closed quantum system. The state of a closed quantum system can be described by a ket psi, which is a complex vector on a Hilbert space, on some Hilbert space H. And to this Hilbert space, we can associate a scalar product of any two vectors on that space, which is denoted on the right in the angular brackets. And in turn, we can define the norm of a state vector as the square root of the inner product of psi with itself. So the natural interpretation associated to the norm of a state is that it gives you a measure of the length of this vector on H. Okay, so assuming that this Hilbert space is separable, then there exists a finite orthonormal basis denoted in those brackets as phi of alpha, satisfying the orthonormality property that the inner product of any two of these basis vectors is the Kronecker delta. And if we make this assumption that the Hilbert space is separable, then this implies that there exists a unique decomposition of any state vector, which is given by the expression at the bottom of the slide. So in other words, what we're saying is that any state vector psi can be represented as a linear combination of these basis states weighted by coefficients which are given by the inner product of psi with the corresponding basis state. Okay, so that relates to states. We can also talk about observables, and measurable quantities of a closed physical system can be represented by linear self-adjoint operators in the Hilbert space. So in general, operators are defined as linear maps between two different Hilbert spaces with particular bases. So following from that kind of general definition, we can introduce the idea of a self-adjoint operator. So a linear operator R, which is this map that I mentioned, is self-adjoint if its domain coincides with the domain of the adjoint operator denoted by this kind of R dagger, and if this relation, so R acting on phi is equal to R dagger acting on phi, is satisfied on the common domain. Okay, so this is kind of technical at the moment. Yeah, so the one of the kind of most important ideas when we talk about the statistical interpretation of quantum systems is using the spectral theorem. So the spectral theorem states that for any self-adjoint operator R, there exists a unique spectral family E of R such that the operator can be written in the following way. So what's given in the blue box, and the spectral family E of R defines a one-parameter family of commuting orthogonal projection operators. So again, this is just quite technical points, and at the bottom I list some of the general properties of this spectral family. So the spectral family is increasing, it's continuous, and it satisfies the following limits at the bottom. Okay, so this is kind of quite of a formal introduction of the spectral theorem. So to kind of maybe think of a more, or to provide a more intuitive understanding of the use of the spectral theorem, we can think of the following example. So the simplest example of a self-adjoint operator is an operator that has a purely discrete spectrum, and which can be obtained from the following eigenvalue relation given at the top of the slide. So just to define some of the things in this equation. So R is again our self-adjoint operator, and phi is the eigenvector, or one of the eigenvectors of R, and Rn is its corresponding eigenvalue. So just to note as well that there are two indices labeling each of the eigenvectors. So this is just to account for any potential degeneracy in the system. So by degeneracy, I mean that out of the full set of eigenvectors of R, there may be a subset of eigenvectors which have the same eigenvalue. But we can simplify it further by just assuming a non-degenerate an operator with a non-degenerate spectrum. So we can just suppress the K label, and we can then define a projector on the eigenspace with eigenvalue Rn in the following way, and we can see that this satisfies the properties of a projector, since so this pi squared, this projection operator squared, just returns itself. So you can verify that by exploiting the orthonormality of the eigenvectors of R. And similarly, you can show that the sum of the sum over all projection operators returns the identity. And that just follows from the fact that these eigenvectors form a basis on the Hilbert space, and the identity is just diagonal in any basis on the corresponding Hilbert space. Okay, so in this example, we can then define a spectral family E of n in the following way. So it's just the sum of the projection operators up to some value r. And indeed, we can see that when lowercase r goes to infinity, we just get a sum over all projection operators, which gives us the identity, which is one of the properties I gave on the previous slide. And we can then write the spectral decomposition of a self-adjoint operator in the following way at the bottom of the slide. So this is just a sum over these projection operators weighted by each of the eigenvalues Rn. So this is perhaps the more commonly used example of the spectral theorem when applied to self-adjoint operators that I'm assuming most people are familiar with. Okay. So actually, shall I ask if there are any questions at the moment, or?
So far, there is no question.
Okay, sure. Okay, so following from these kind of formal definitions, I can now talk about how we can apply these ideas to kind of formulate the statistical foundations of quantum mechanics. So so consider a statistical ensemble E consisting of a large number of identically prepared quantum systems, which we can label S1, S2, all the way up to Sn. Then the first postulate one of the ways that we can introduce the first postulate of quantum mechanics is by saying that a complete characterization of this ensemble E is provided by a normalized state vector psi in the Hilbert space pertaining to the quantum system. So by normalized state vector, we mean that the norm of the ket psi is 1. Okay. Yes, I don't think I have anything else to say on this. Yeah. So the second postulate we can similarly introduce. So the second postulate tells us that the measurable quantities of this ensemble are represented by self-adjoint operators in the Hilbert space, and the outcome of the measurement of a particular observable is represented by a real valued random variable R with a cumulative distribution function given as follows. So what this implies, so this is quite a mouthful, but what this implies is that the possible outcomes of any, if we basically perform a measurement on our system, then the possible measurement outcomes that we can obtain when we measure a observable R, then are given by the eigenvalues of this observable. So this lowercase r. Okay, and then this cumulative distribution function is just a quantity that comes from standard classical probability theory. Okay. So similarly, we can from the second postulate we can define the mean value of this random variable, which is which is just given by the integrals on the top line, and we can re-express this in the form on the right-hand side, which is probably the form that most of you are familiar with, that the expectation value of some observable is just equal to the corresponding, or to the operator representing this observable sandwich between the ket and the corresponding bra vector. And okay, so the variance can also be defined in the way that we can from classical probability theory. So yeah, this is just the expectation, or the mean value of R squared minus the square of the mean value. Yeah, so these are just kind of standard formulas. Okay. So far we've been talking about pure states. So to define really what a pure state is, we can introduce the kind of a generalization of this to what are called mixed state or statistical mixtures. So as I kind of mentioned from the first postulate, the state vector psi gives a complete characterization of this ensemble E, which is made up of many identical copies of our quantum system S. So we can define a more general type of quantum statistical ensemble. So consider a number M of ensembles, which we can label from E1, E2, all the way up to EM. And to each of these ensembles, we associate a state vector, or ket psi alpha, with alpha being labeled 1, 2, all the way up to M. Then the total ensemble can be obtained by mixing all of these sub-ensembles with weights W alpha, which satisfy the following properties given on this slide. So we assume that these weights are non-negative and that their sum gives 1. And in practice, the way that we can, this is kind of a generic formal way of defining a statistical mixture. But in practice, what we can do is we can take a large number. So we can take a large number of realizations, n of alpha, from each sub-ensemble E of alpha, and we can then define these weights W alpha as the ratio of the number of realizations in each sub-ensemble divided by the sum of the realizations across all of the ensembles. So perhaps a slightly more intuitive way of introducing the idea of a statistical mixture is to think that, well, when we perform a measurement on a quantum system, so if we want to measure some observable which is represented by a self-adjoint operator, what we're doing is, or what happens is that, just according to the standard rules of quantum mechanics, we obtain a measurement outcome which is represented by one of the eigenvalues of this observable that we're measuring, and our state collapses to one of the possible states, which is given by one of the eigenvectors of this observable. So when we're talking about, so this is for pure states, when we're talking about statistical mixtures, what we're doing is we're kind of mixing the ideas of both classical and quantum probability. So when we perform a measurement of an observable, there's kind of a layered effect. Or this is the way that I'm not sure if this is the best way to explain it, but this is just the way that I envisage it, is that there's this layered effect in that what happens is that we perform a measurement of some observable, then what happens with this measurement is we're effectively picking we're performing a measurement on one of these sub-ensembles, and then within each sub-ensemble we basically obtain a measurement outcome with a probability which is determined from the corresponding ket psi of alpha. So in this way, what our statistical mixture kind of represents is the extra uncertainty that may be involved due to there being some extra type of classical noise in our system, or there may be some uncertainty in the way in which our state is prepared. Okay, hopefully that makes sense, but just feel free to ask questions if anything I'm saying it's not making sense. Okay. Okay, so just to introduce some more statistical formulae. So when we're talking, so now we're talking about statistical mixtures, not just pure states. So according to classical probability theory, the cumulative distribution function that I introduced in the previous slide can now be written in the following way. So it's just rather than just being the sandwich between, or the sandwich of our ket psi with the spectral family E and the corresponding bra is now a sum over all these kets belonging to each subensemble, weighted by this coefficient W of alpha. And similarly, we can define, so this is just, again, this is just taking formulas from the previous slide and generalizing them to statistical mixtures. So the mean value of this random variable can also be defined for a statistical mixture in the following way. And with the help of this definition, so what we can do is we can define a so-called density matrix given by this formula in the blue box. And then using this definition, we can write that the cumulative distribution function is equal to the trace of this spectral family E of R multiplied by the this state rho. So yeah, so for those of you for those of you who may not be familiar with the trace operation, all you're doing when you're taking the trace of something, you're well, I guess maybe the best way to introduce the idea of a trace is that if you think of a matrix, when you perform the trace of a matrix in any basis, what you're doing is you're basically summing over its diagonal entries. So in this case, what you're doing, one way of expressing that is by summing over the, well, you can sandwich the quantity inside the trace by one of the eigenvectors, or say we have a particular set of basis states that I introduced at the beginning. You can sandwich the quantity inside this trace by one of these basis states, so one of the ket states with the bra states, and then you can sum over all the states that belong to this basis, and this basically just defines the trace. Okay, so I think is there a question? Yeah.
Yeah. Sorry, can you please just need to clarify on how we are getting this W alpha, how the ensembles and C's are mixed?
Okay, how's the best way to explain this? So they're mixed. Okay, so in the earlier parts of this talk, I was just talking about a single a quantum system, which is just whose state is just described by a single ket, so a single complex vector, which we call psi. So what we mean when we say statistical mixture is that rather than just the state of our system being described by a single ket, it's described by a statistical mixture of kind of many kets. So rather than just think about one ket, there's many kets, and what these weights do is essentially provide the degree to which we're mixing all these different states, right? So so the reason that these weights have to be positive or non-negative is that we can potentially think about these weights as corresponding to probabilities, and similarly, the reason that these weights have to sum to 1 is because they can potentially be interpreted as probabilities from what's been provided at the bottom of the slide. So does that answer? I'm not sure if that answers the question. I can maybe talk a bit more if that doesn't. But
I don't know if it doesn't answer the question. The Martin can kind of ask it again, or kind of ask to clarify something else. I think you can go on.
Okay. Actually, it might be good just to give like a very basic example of what I mean by statistical mixture before going on, just to kind of clarify. So, okay, so yeah, just to give like just a basic example. Suppose like we have a I don't know, like a black box, and when we press a button on this black box, it generates a quantum state which can be described by a ket, so a ket vector. If we, so in like an idealistic case, we can assume that this black box is perfect, and that every time we press the button, we return a state vector which is always given by psi. But what we could do is we could assume this kind of black box is imperfect. So this could be used to model like an experimental, I don't know, like an experiment or to some form of realistic device where you want to prepare a quantum state. But so say when we now press the button on this black box, instead of just giving us a single possible state psi, it could potentially give us another state. Let's call it, I don't know, let's say state 1 is psi 1 and state 2 is psi 2. So if we assume this black box is imperfect, when we press the button, we could get either psi 1 or psi 2, but we don't know which one, unless we perform some measurement on the system, we don't know which state we've been given. So in the first case, when we have a perfect kind of black box, we can describe the state of our system without needing the use of statistical mixtures. We can just define its state using a single Ket vector. In the second case, because there's this additional uncertainty, like we don't know if we have state psi 1 or psi 2, we have to introduce the idea of a statistical mixture. And what the statistical mixture reflects is the fact that we could be given psi 1 with a particular probability, and we could be given psi 2 with 1 minus the probability of whatever we're given psi 1. So essentially what these weights do is they kind of, so in this case, these weights would correspond to the probability that we either get given psi 1 or get given psi 2. So in this case, there would be two weights. We can call them W1, W2. If the probability of getting state 1 is psi 1, then weight 1 would be P, let's just call it probability P, then the weight 2 corresponding to the second Ket vector would be 1 minus P. So essentially what these weights do is they introduce this extra layer of uncertainty that reflects how our state is prepared. So, okay, sorry if I went off on a bit of a tangent, but I just want to kind of make it, hopefully that's kind of clear, but just, yeah, feel free to ask any other questions.
Okay, there is a clarifying question from Martin again. I think this one is more specific. Is W alpha is equal to psi alpha multiplied by the epsilon alpha?
No. So no, because the epsilon alpha just represents an ensemble. So epsilon alpha isn't a state. It's a kind of mathematical construct that defines an ensemble. So the way that we can represent, a way that we can represent the state is by using, for a state which defines a statistical mixture, is using this formula that's in this blue box. So it would be the weights multiplied by the outer product of psi alpha with its corresponding bar vector. So the reason that you have to define the state in that way is because you can't just write down, you can't just write down the state as like a sum of weights multiplied by single Kets, because that introduces a contradiction in how you kind of construct the state. Because as I kind of mentioned before, a Ket is normalized to have, for the fact that when we write down a Ket, each of the possible states that our system can be in, okay, psi can be expanded as a linear combination of states that represent all the possible states that our system can occupy, and each of these are multiplied by coefficients, the modulus squared of which gives us the probability of measuring the system in the state when we perform a measurement on the system. So the reason that we can't just write this as a sum of Kets is because it would kind of be combining the ideas of, it would be mixing the ideas of classical and quantum probability in a non-consistent way. So we have to kind of, inside these kind of psi of alphas is contained the quantum probability of measuring a Ket within a particular subensemble, and then we're mixing these according to these weights W alpha. Yeah, I'm not sure if that gives a good explanation, but yeah, should I just carry on, or?
Yeah, I think we should just continue,
okay.
And maybe it will be more clear later. Thank you. Okay,
yeah, sorry. Yeah, hopefully that maybe gives a better understanding, but yeah, okay. Yeah, so just the kind of takeaway, idea really of this slide is that you can represent the state of a quantum system, or you can represent the mixed state of a quantum system in using the formula that's given in this blue box. Okay. Okay, so for this newly defined state that we've introduced, so this what I've called a mixed state phi, which is a sum over these alphas multiplied by the psi alpha ket and multiplied by its corresponding bra, then we can define the mean of this. We can define the mean of an observable in the following way. So it's the trace of the observable R multiplied by the corresponding mixed state. And similarly, we can define the variance again, just using that the variance is equal to the mean of the square of R minus the square of the mean of R. Okay, so what these formulas imply is that the total ensemble, which was given as which comprises each of these individual sub-ensembles, is completely characterized by this density matrix, this mixed state rho. And some important properties of this state rho is that firstly it has to be Hermitian. So it has to be this adjoint, so this operation that I introduced at the beginning, this dagger operation, rho dagger has to equal itself, and rho has to also be a positive operator, and that the trace of rho has to equal to 1. So the reason that we require these properties is that each, as I kind of mentioned previously, each of these weights can correspond to a probability of us measuring the system within a particular sub-ensemble. So the reason that we require rho to be positive is that if it was non-positive, then we could potentially have negative things like negative probabilities contained within our state, which obviously doesn't make sense. Similarly, because these weights correspond to probabilities, then we require that the trace of rho is equal to 1. So the way that you can think about this is that when we perform the trace of rho, what we're effectively doing is summing over each of the weights multiplied by some quantity, which is like modulus squared of psi of the inner product of the modulus square of psi of alpha, with some basis vector. So the reason that this has to be trace 1 is because the fact that this state contains probabilities and has to be normalized. Okay, and we can also represent rho using its spectral decomposition. So in this case, these P of i's, yeah, so actually you could probably use a spectral decomposition to explain these properties rather than the way that I explained it. But to kind of justify these properties of rho, you can take the spectral decomposition of rho, because, well, it's an operator, and if it's a Hermitian operator, then it emits a spectral decomposition. So basically, we can write it, if it has it's an operator with a discrete spectrum, so we can write it as a sum of its eigenvalues, pi multiplied by these basis vectors, which are kind of the psi symbol, phi, the var phi symbol, in that way. And then we can use a spectral decomposition to justify these properties of rho. So the fact that these P of i's correspond to probabilities, so therefore the trace of the rho has to be 1, it has to be positive, and it has to be Hermitian. Okay. So one of the discerning features of a mixed state is, or one way that we can discern a mixed state from actually what I should say is that a mixed state is one in which in this sum that I've given on this slide, where we have more than one index in this sum. So we're summing over multiple indices. And a pure state can be written as one which there's only one index, so there's no sum involved. And we wouldn't be writing it in terms of the basis vectors, but we would be writing it as our ket psi multiplied by the corresponding bra vector. So one way that we can discern between what is a mixed state, so if we're just given a density matrix rho, the way that we can discern between whether this state is mixed or whether it's pure is by introducing this this notion of purity. So the purity is defined as the trace of rho squared, and if the trace of rho squared is less than 1, then this defines a mixed state. Whereas if the trace of rho squared is 1, then this defines a pure state. So actually, yeah, at the bottom of the slide, you can see that rho is, for a pure state, rho can be written as just this quantity. So psi multiplied by bra psi. Okay. Okay, so I think I have enough time to just quickly introduce composite systems. So, okay, yeah, I think I should leave just questions to the end, I think. Okay, so as I kind of mentioned at the beginning, composite systems, when we think about open quantum systems, the kind of the starting point is to really introduce the idea of a composite system, since in order to describe a system which is open, we need to describe both our quantum system of interest plus its environment. And so to introduce the idea of a composite system, consider two quantum systems which we label S1 and S2, and each of these can be associated with Hilbert space is H1 and H2. Then the way that we can describe a state on this composite system is by noting that the Hilbert space of both associated to both or the Hilbert space associated to the total system, so S1 plus S2, is given by the tensor product of the individual subsystems. So it's the Hilbert space of this composite system is equal to the tensor product of H1 with H2. And using this property, we can then write that a general state in this Hilbert space can be written as or can be expressed in the following way, where each of these Ket vectors var phi of 1 and var phi of 2 correspond to the basis, or correspond to a set of basis states on each of the subsystems H1 and H2, and then these alpha of ij just correspond to coefficients, essentially. Okay, so similarly, so this is how we can define a general state on this composite space. We can do the same with operators. So any operator on H can be defined again using this tensor product, this tensor product construction. So we can write that any operator A is equal to the sum over some operator A1 on the defined on the subsystem, which or an operator A1 which acts on the subsystem A1, tensor product tensor product multiplied by a operator acting on the subsystem on the second subsystem. And an important feature is that when we think about acting these operators on states, a general property is that say we act an operator which is just given by A1 product A2 on some state which is given inside this bracket, then the way that we perform this operation is that we each operator only sees its corresponding state on the defined on the relevant Hilbert space. So what I mean by that is that when we multiply this bracket through, the operator A1 only acts on the state var phi of 1, and A2 only acts on the state var phi 2. Okay, so these are just some kind of general properties of composite systems. And okay, so if these two subsystems, say these two subsystems are uncorrelated, then the way that we can write down the density matrix for the entire system, so S1 plus S2, can be this density matrix for the entire system can be written in the following way. So we write it as the tensor product of a density operator on defined only on the first subsystem multiplied by the density operator defined on the second subsystem. Okay, and so for two subsystems which are uncorrelated, we can then write that that if we want to calculate the mean or the expectation value of an operator which is given by the tensor product of A1 and A2, then just using some formula that I introduced in the previous slides, we can write this as the trace of A1 multiplied by A2, tensor product multiplied by A2, and then multiplied by this density matrix rho. And bear in mind here that the trace is taken using a basis which is defined on the composite space. So this is defined on the full Hilbert space, which contains both systems S1 plus S2. So what we can then do is that using the fact that these for two subsystems which are uncorrelated, we can write this expression on the top line, or the way that we can simplify the expression on the top line is by essentially using the property that I introduced on the previous slide, where I had two operators acting on some state. So we can use that property to then show that this trace breaks into two parts. So the first part basically is written as the trace taken over subsystem 1, and the second part is written as the trace taken over subsystem 2 with whatever is contained within the curly brackets. And then we can just use the fact that the mean of a operator defined on subsystem 1 is given by this first trace, and the mean of an operator on the second subsystem is given by the second trace. So we can just write it as the product. So for any two subsystems which are uncorrelated, we can write the expectation value of this operator in the top left using in this kind of product form of just the expectation value or the mean of this operator A1 multiplied by the mean of operator A2. Okay.
Sorry, Graeme.
Yeah.
There is a logical question about your previous slide. Can you please go back?
This one or the previous?
How to define correlations between two systems?
So do you mean, okay, is there anything else in that question?
No, I mean, like you say that if S1 and S2 are uncorrelated, and you write rho is equal to rho 1 tensor rho 2, what do you mean uncorrelated?
So uncorrelated in the sense that, yeah, that's a good question. So uncorrelated in the sense that that if we perform, okay, maybe there's a better way to, okay, so I mean uncorrelated in the sense that if we perform a measurement in any of the subsystems, say S1 or S2, then a measurement that we perform on one subsystem doesn't affect the measurement that we perform, or it doesn't affect the measurement okay, so let me phrase it this way. So yeah, say we perform a measurement on our composite system. If we measure subsystem 1 and get a particular measurement outcome, and then we measure subsystem 2 and get a particular outcome, if they're uncorrelated, it means that if the density matrix is uncorrelated, it means that the first measurement outcome we obtain is in no way correlated with the second measurement outcome, I think, if that's what the person asked.
So is it disjoint then?
What do you mean by joint?
Disjoint. I mean, I don't know. That's the
Oh, disjoint. Oh. I'm not sure what you mean by disjoint.
Okay. No, but maybe you can say things like, you know, if the system, I don't know, row 1 and row 2 just don't entangle with each other, in that case, they can be written like this, yeah? Or if you prepare them separately and just describe together,
yeah.
So they also could be written like this.
Yeah, so, I mean, systems can be also classically correlated, so they don't necessarily have to be entangled, but yeah, I guess intuitively you can think of these two systems, when these two subsystems are uncorrelated, they you can't obtain any information about one subsystem from the other, right? If you perform just a measurement on one of these subsystems, you can't learn anything about the other one because they don't share any kind of information. I think that's maybe a better way of explaining it.
Okay, thank you.
Okay.
Yeah, the person is happy with your answer.
Okay, good. Okay, yeah, so I think we're probably coming to the end of the lecture anyway, but let me just quickly, I'll probably just skip out the bit on the end on quantum measurements, but just finish up with composite quantum systems. So, okay, so for observables of if we want to define an observable just on one of the subsystems, the way that we can define it is by defining an observable A, which is just the tensor product of a observable on a subsystem, say A1, with the identity on the other subsystem. In a way, you can kind of think of this as a kind of effective dilation. So what you're doing is you're defining an operator on one of the subsystems, and then you're kind of dilating it to act on both of the on the total Hilbert space, which comprises both of these systems. But we because we only want this to be defined on one of the subspaces, we tensor product this with the identity. Okay, and it's so to then define so to then characterize the kind of statistics of either one of our subsystems. Let's just say subsystem 1. We can introduce what's called a reduced density matrix. So a reduced density matrix is a density matrix of a composite quantum system, which we've taken the partial trace over. So what we can, in order to define the density matrix of one of the subsystems, we can specify the density matrix of our entire composite system, and then trace out any information on one of the subsystems that we don't care about. So in this case, we can define the reduced density operator, reduced density matrix for subsystem 1 in the following way. And so basically with this definition, what you can show is that the mean of any observable, the expectation value of an observable, say A, defined at the top, can be written as as using this trace. So this corresponds to what we defined when we were just talking about non-composite systems, i.e. we could define the expectation value of an observable just as the trace of the observable multiplied by the corresponding density matrix. So what we're basically saying here is that when we're dealing with composite systems, when we trace out one of these subsystems from our density matrix, we obtain a density matrix which is capable of completely characterizing the statistics of one system in such a way that is consistent with if we were only interested in one of these subsystems. So we weren't considering a composite system, but just looking at one of these subsystems. Okay, I'm not sure if there's, okay, maybe based on, should we maybe end it here based on time? I mean, I'm happy to quickly go over this slide, but just in case if there's any time constraints.
Yeah, Graeme, I think it would be a nice point to stop for today. So thank you very much. for the very nice introduction. Ilya, are there more questions for Graeme?
So far, there are none. So there was a few during the talk, but I hope we addressed them as much as we could.
Okay, okay. Then maybe we can ask Graeme maybe give us a very short preview of what he, maybe just in 1 or 2 sentences of what he's planning to do next week, so that we can just give people the chance of thinking for a second. And if nobody has further question, we can stop then here. So Graeme, what are you planning to do next time?
So next time I plan on hopefully applying what I've introduced to you today to actually to kind of develop some of the basic ideas in open quantum systems theory. So I appreciate today that it was mostly just kind of background material, but in next week's lecture, we'll actually start talking about the theory of open quantum systems and introducing some like the basic concepts related to that.
Perfect. Thank you very much. So Ilya, it doesn't seem like there are further questions. So Graeme, then thank you so much for a very nice introduction. And I think all of us are looking forward to the next lecture next week, which will be again next Tuesday at the same time at 2 o'clock. So Graeme, and we will post the video on YouTube just now. And like we did for the previous schools, I will have to discuss with Graeme when we do that, but we will organize a quiz so that we can distribute certificates of participation. Yeah. So thank you very much for joining us today, and all the best. And we will see you latest next week. Yeah. Thank you, Graeme, and thank you, Ilya, very much for organizing the moderation of the questions. So thank you very much. See you next week.
Okay, thank you.
Thank you.
Bye.
See you next week. Thank you. Bye.